Good morning, students. Welcome to lecture 7 of module 4. So today let us see how a BJT can be used as an amplifier. Now, amplification, it is the process of increasing the signal strength by means of amplitude, or amplifier is a circuit or an electronic device which is used to increase the amplitude of a given signal, or it is an electronic circuit which strengthens the weak signals. Yeah. Now, how can we use a particular transistor as an amplifier? Now, transistors can be used as an amplifier when it is operated in the active region, or so called the linear region. Now if you see the particular circuit to make a transistor operate as an amplifier, now you can see here that we have a AC supply connected in series with the RB resistance connected to the base of the transistor, and to the collector we have the resistance RC, which is connected to the collector of the transistor and given to a DC source plus VCC. And similarly here we have another DC source, that is plus VBB. Clear? Now here this DC source and your AC input Vin will superimpose each other. Now let us just see, since we have taken NPN transistor, we can see the current directions. The current IB is moving into the device, and even current IC is moving into the device, and current IE is leaving the device. So we know that IE is equivalent to IB plus IC, right? Now in the circuit you can see an AC input and the DC bias voltages which is going to get superimposed, that is this particular DC voltage, that is VBB, and your AC input, that is Vin, which will be superimposed. Clear? Now if this is my particular input, right, if this is my particular input, now we can see this is my particular zero reference line, but since I'm adding certain amount of DC bias to the input, my input will be a little bit DC shifted. You can see the input of this particular order, right, and my output will be amplified and also 180-degree phase shifted. Why? Because when you give input to a common emitter configuration, we already saw that there will be 180-degree phase shift between your input and your output. Clear? So since this particular circuit is operating as an amplifier, it will amplify your input signal and also it will phase shift it by 180-degree. Clear? Now we'll see how this particular circuit is working. Now we know that the common emitter configuration is used and the transistor will operate as an amplifier, right? And we also know that the current amplification factor or the current gain for the common emitter configuration is given by beta, which is equal to IC by IB. And if I rearrange the equation, we can see it is IC is equal to beta into IB, right? So if there is any small change in IB, you can see that there is a large change at the output current IC. So a small change in the base current IB produces a huge change in the collector current IC, because IC is equal to beta times IB. Now, so we also know that IE is equal to IC plus IB. If IB is very small, then IC is almost equivalent to IE. And in the figure, and in the figure, an AC voltage Vin to be amplified is superimposed on the DC bias voltage VBB with the base resistance RB in series, and the DC bias voltage VCC is connected to the collector through the collector resistance RC. So you can see here the particular point what they're saying is the AC input Vin to be amplified, which is the input voltage to be amplified, will be superimposed with the DC bias voltage, that is VBB, which is connected to RB, and the DC bias voltage VCC is connected to the RC resistance. That is the input which I wanted to be amplified, the AC input is superimposed with the DC source in series with the RB, and the DC bias voltage VCC is connected in series with the collector resistance. Now the AC input Vin produces an AC base current, that is IB, which results in much larger AC voltage across RC, and this voltage is amplified an inverted version of the input voltage as shown in the figure B. Now whatever particular input voltage, right, this particular input voltage will produce one base current IB, and that particular base current IB into beta times is your IC current, and that particular IC current, when it flows across the RC resistance, it will give out one particular amplified voltage and the inverted version of the input voltage. That is how you can use this particular device as an amplifier. So if you see here, when this particular input voltage will induce one IB current, and we know that IC is beta times of IB, so this particular current will be very much in magnitude when compared to IB, and when this particular current flows through this particular resistance, IC into RC will produce a output voltage which will be amplified and inverted version. So this is how you can use the particular transistor as an amplifier for both the current amplification and the voltage amplification. Now if we move further, now if I have to write the AC equivalent circuit using the same particular circuit, an AC equivalent circuit can be represented by making DC bias sources equal to 0. That is, we will make in the corresponding circuit, that is VBB equal to 0 and VCC will be 0. So if you see here, only the AC input is present, and we don't have our VBB and VCC DC sources here. Now the DC bias sources ideally will appear as short to the AC voltage, clear, and the forward biased base emitter junction presents a very low resistance to the AC signal, clear, and this internal AC emitter resistance is designed as RE dash here, that is your RE dash, and the AC emitter current is given by this particular AC emitter current, that is your IE current will be almost equivalent to IC, which is given by VB by RE. So this particular emitter current, we know that it is almost equivalent to this particular collector current, and it is given by VB by RE dash. Clear? And the AC collector voltage is equal to the AC voltage drop across the resistance RC. So voltage across RC is VC, which is equal to IC into RC, which is our output voltage. Now here also we know that IC is almost equivalent to IE. Now we will write the particular equation for VC, which is equal to IE into RC. Now, if in case you want to calculate the particular input voltage, it can be calculated by VB, which is equal to V in minus IB RB, which is your input voltage. Now we know that voltage gain is given by output voltage by input voltage, the ratio of VC to VB. So the voltage gain is output voltage, that is your collector voltage, divided by the input voltage, which is your base voltage. We have already calculated, that is VC is equal to IC into RC, and VB is equal to IE into RE. Now if you substitute this particular thing, we know that IC and IE are almost equal. So if you cancel out each other, the current gain is given by the current gain is given by the sorry the voltage gain is given by output current, output voltage by input voltage, and we know that output voltage is given by IC into RC, and VB is given by IE into RE dash. So if you substitute this particular equations, we know that IC and IE are almost equal. So we will get the voltage gain formula as RC divided by RE. Now since RC is always larger than the RE dash, the gain, that is output voltage, is always greater than the input voltage. Clear? So this completes today's topic. We'll meet in the next lecture.